Emmanuel, sir, there is confusion in the audience. Please make some announcement that event is not yet started.
Yeah, sure, sir. Uh, Good afternoon. I am Vineet Sahula at MNIT Jaipur. We are soon going to start. Till then, the speakers and the sound is muted for that part. We are waiting for some dignitaries to join. Thank you for joining to you all.
A very good afternoon to all of you. I'm very sorry for the slight delay. We were trying to connect some of the experts, and some of them there was a technical glitch. Sorry for the inconvenience. It's a joy for me to welcome all of you on behalf of MNIT Jaipur Electronics and ICT Academy, and also on behalf of our director, Professor Narayan Prasad Padi sir. We are just wanting that he would join and welcome you so that we'll start. It's a joy for me as this is a very special occasion because we have so many esteemed dignitaries with us, and I would like to welcome Professor D.G. Sitaram, Chairman of AICTE, Dr. J.B.V. Reddy, Head of Quantum Technology Cell, Mr. Sandeep Patel will be joining shortly. We have Professor Padi also will be joining shortly. There was some technical glitch. I'm sorry for that. Dr. L. Venkat Subramaniam, IBM Quantum India leader. Welcome, sir. Dr. Mustafizur Rahman, who will be our speaker, and he's a research scientist with IBM Quantum. Dr. Mani Madhukar, who is with us, with the program lead of IBM Innovation Center for Education. Ms. Nivedita De, who will be our main resource person. She is joined. She works with PricewaterhouseCoopers Quantum US R&D. Dr. Ashwath Babu, Assistant Professor, IIT Dharwad, IIT Dharwad, PhD from IIT Kanpur. It's a joy that we are all here, and they are my colleagues. Some of them have joined, chief investigators in the Electronics and ICT Academies. I can see Aparajita Oja ma'am, Professor Aparajita Oja, Professor Vineet Sahula, and Professor Srihari Rao Matri have joined. My colleagues are here, Professor Namita Mittal, Head of the Department, Computer Science and Engineering, MNIT Jaipur, Dr. Mahipal Jadeja, who is the Joint Principal Coordinator along with me, and also we have Dr. Rajiv Arya, who is joined from NIT Patna. It's a joy that we are all here, and I want to welcome you to this faculty development program on quantum technology applications. The program is aligned with the curriculum, the minor curriculum on quantum computing, which has been recently released and approved by AICTE and DST together, with the support from IBM and other agencies like CDAC. It's a joy that we are able to conduct a series of programs through Electronics and ICT Academy. This time we would like to welcome all the dignitaries who have joined, and it's going to be an exciting time. It's only 2 hours per day, but it's going to be for 20 days. So that's a long time, but then 2 hours so that we will be able to assimilate more information. We can revise. We will assure you that we will share the recordings on a day-to-day basis and also the slides. We are looking forward for this National Quantum Mission has a great agenda with 4 verticals. So we will start with the 4 verticals in this main program today on the quantum technologies and applications. So the 4 verticals, in fact, we're going to start immediately after this inaugural session. We will start with the understanding the 4 verticals, and hopefully we will cover detailed courses in these 4 verticals and with also both software and hardware labs. So we're looking forward for a time of about 6 to 8 programs running till I think till December. Dr. Mani Madhukar will be sharing more information about it. At this time, I'm very happy to share with you about our guest today. So I would give this time to Professor T.G. Sitaram, who is the chairman of AICTE, and also he was former director of IIT Guwahati, a very learned academician, and the actual brain behind this minor course on quantum computing at the UG level, which will be floated in many AICT affiliated engineering colleges shortly. So I would request Professor T.G. Sitaram, sir, to share a few words of wisdom. Thank you, sir.
Namaskar. Very good afternoon to all of you. First of all, let me congratulate the entire team from DST, AICT Academy, and IBM, and many other, who are speakers on this today. First, let me give them a congratulations. It's a big thing because it's the first time. So I see very prominent figures here. I'll just read out some names which I have. Dr. L. Venkat Subramaniam from IBM, Dr. J.B.V. Reddy from DST, Dr. Mustafir Rahman, Dr. Mani Madhukar from IBM, Ms. Nivedita Dev from PwC, and Ashwat Babu from IIT, and many others, all AICT coordinators from all the AICT Academy are here. I'm very happy to launch the quantum technologies and applications training program. I'm also happy to see it is not just restricted to the teachers. It's also, you have invited students and faculty members and also some industry representatives also taking this course. So it's a first in the series training program aligning to the courses as the previous speaker said. All India Council for Technical Education approved minor degree course curriculum. So anyway, warm greetings to all the dignitaries and the esteemed faculty members, experts from both industry, academia, and also partner institutions for this FDP, and dear participants of this event. I see quite a large number, close to about 540 people are already registered. They are on the portal. So it gives me immense pleasure to inaugurate this faculty development program, but it encompasses even others, as I told you earlier, on quantum technologies and application. This is the first in the series, as I told you earlier, training program designed to equip our educators with cutting-edge knowledge and skills in quantum computing. So this is an initiative, when DST, Dr. Reddy and other team, and including the chairman of Quantum Mission and also Secretary DST Abhay Karandikar came to us and said, let's develop this. So our team put up the experts with Professor Ghosh from Indian Institute of Science, with a series of experts who developed this minor degree in quantum. So they have 11 or more than 11 courses. So our actually detailed curriculum has been defined. I feel this is one of the very state-of-the-art curriculum. So based on that, now today we are here in collaboration with MNIT Jaipur, NIT Patna, IIT Roorkee, IIT Guwahati, IIT, DM Jabalpur, and IBM come together to really share rich knowledge in the quantum technologies and its applications. And I call this as a significant step towards empowering our youth to lead the future of technology and driven education. And our vision, AICT vision in this is quantum technology is no longer just a theoretical concepts which physicists is to pursue, but are becoming integral and technological landscape. So influencing sectors from cryptography to communications and sensing to computing. Recognizing its transformative potential, AICTE envisioned the integration of quantum technologies into our educational curriculum. We look at the bold step of launching India's first minor degree program in quantum technology. We are already sent out a Google form, and more than 100 institutions have volunteered to offer this program at their institution. So what is required is, good. Now curriculum is ready, but good textbooks are required, and then experienced teachers are required, and more than that, an experiential laboratory is also required. So this is where we are already started working in collaboration with DST. I would like to tell you, recently we had a meeting with Secretary DST, where Dr. Reddy was also present. He will elaborate on that, wherein we have come to a sort of a discussion. At least 25 of the Center for Excellences in quantum technologies will be developed at engineering colleges so that they can share this facility and learn an experiential learning, not just theoretical concepts. So I would like to thank DST for taking this initiative and under the visionary framework of the National Quantum Mission. This pioneering move not only places India at the forefront of global educational innovation, but also prepares our students to excel in the emerging quantum era. Why this is important? As I told you, today, if you look at, it is not just our IITs, which are definitely institutes of Indian technologies they have created, but there is a large number of other pool which we don't recognize many times. That is the engineering college students. The scale at which we are producing engineering graduates is mind-boggling. Today, engineering graduates coming from AICTE approved engineering colleges are about 1.5 million per year, and it is not just this year. From last 10 to 12 years, they're continuously coming. Because of this, we were able to see our engineers across the world. I'll say any company you name it, an engineering graduate, even most of the 85 to 90% of the faculty at IITs also are having a degree from one of those engineering colleges. But when you ask them, they will tell you, I did an MTech from IIT Madras, PhD from somewhere else abroad, but postdoc, but they will never tell you where did they graduate. They all graduated, most of them from engineering colleges, like even me. So this is what we have to realize. We need to change the narrative. There is a lot of talent in the rural part of India where there is a lot of. So for them, we need to equip with latest technologies. This is the attempt. So the journey of bringing quantum technologies to the classroom does not end with curriculum design, as I told you earlier. The key to successful implementation lies in the hands of our educators, that is teachers. That is why AICTE is deeply committed to faculty development, especially in emerging technology. And also, as I told you, this technology to be taken to the each and every corner of the country so that there is an accessibility for a poor student who is hungry to learn and deliver something. So these technologies are going to transform their life, not only their life, around them, and also in turn the nation. We recognize that our teachers must be self-sufficient, confident, and knowledgeable to impart complex concepts effectively. So this one kind of training program and drives us to consistently, take this cutting-edge technology to all faculty members ahead. They can be put ahead of the curve. So the importance of the capacity building, I don't need to tell to AICTE Academy, because I was also part of as a director of IIT Guwahati. We had an AICTE Academy which has trained a large number of teachers in the Northeast, and which is a really a commendable job they have done in Northeast in the digital technologies. So to prepare our educators here, the expanded role, AICTE emphasizes a comprehensive capacity building strategy. This faculty development program series not just restricted to the teachers, it can be expanded to even industry, because these type of topics are very, very new. So I could see some of the verticals under which the program is going to be organized: quantum computing, quantum communication, quantum sensing, and quantum materials and devices. These modules are crafted by experts from IBM, Quantum, and also PwC Quantum R&D. So this very clearly shows that academia industry interaction is happening very closely in this particular program. And also this is not a very short 1 or 2 days training program. This is 20 days, 40-hour intensive training program. Coming, there are a lot of experts coming from all across. So it's more than just a series of lectures. So it represents a learning journey for all the people who have registered. I can see that now almost 550 plus people have registered for this, and it will also happen through not only just conceptual understanding, it happens through interactive sessions on quantum physics, superposition, and entanglement. So I also understood that from the team, there is a hands-on experience with practical training on quantum circuits, qubits, and quantum communication. So they will also describe the real-world applications, exploring how quantum technologies are revolutionizing the fields like cryptography, healthcare, and AI. So as you all know, AI is disrupting the whole world. In that time, the journey of quantum is not limited to knowledge. This kind of course is not just limited to knowledge acquisition, but extends to beyond the implementation and also innovation. There could be many startups, innovations can happen. So our aim here, collective aim of all these institutions which have come together today, is to empower all of these young people to bring quantum concepts into the classroom effectively, inspire all the people, all the students to pursue research in quantum technologies. I would like to tell you that AICT also has a mandatory today, all our education institutions, 14,000, R&D center as well as Institute Innovation Council, both are made mandatory. So this also will bring in a culture of research and innovation into our technical colleges which are there. And these are the colleges who have given either faculty to IIT or the scientists to ISRO, DRDO, PARC. All of them are not from IIT graduates. They are all, majority of them, the graduates of the engineering colleges. So even though I was a professor at IISc for the last 35 years and director for 4 years at IIT Guwahati, but I have a lot of appreciation for these engineering colleges which have really transformed. So that narrative has to go, ladies and gentlemen. So we need to invest in this capacity of the young people, which is a large number. It's in millions. So we can produce engineers with these newer technologies to the whole world. So we are not only enhancing the quality of education through these programs, but also building a robust foundation for India's future as a global knowledge hub in quantum. Our educators are the torchbearers of this vision. So our teachers have to be equipped at a very high level. And AICTE, I'll tell you, we have trained 300,000, that is 3 lakh teachers already in emerging technologies. Okay, and AICTE programs are offered, in the engineering programs are offered much before many of the IITs in data science and artificial intelligence, cyber security, and even now quantum. We are much ahead of the curve. So as we embark on this transformative journey through these series of training programs, I encourage every participant so to engage fully and maybe ask questions to the experts who are here today with you, and use that opportunity very well, and also strike a collaboration with them and explore the limitless possibilities that quantum technologies are going to bring to you. This is not just an opportunity to learn, but to lead and inspire. So you can, some of you can take it to the next level to do your own startups and entrepreneurial culture, which is now becoming normal in India because we are the 3rd largest ecosystem in the startups. I extend my heartfelt appreciation to MNIT, Jaipur, and all the AICTE Academy, all our IITs, IIITs, and all partner institutions for organizing this FDP activity with IBM, mainly IBM and PwC, and many other industry experts, and more importantly, the DST Quantum Mission, along with AICTE, are putting hands with you. Let us continue to learn, innovate, and lead with courage and vision. Together, we are going to shape the future of education, technology, and society to produce engineers with latest technologies, latest emerging technologies to the whole world. I'd say if you achieve our gross enrollment ratio of 50% by 2035, I have no doubt that our engineers and technologies with latest in these emerging technologies will rule the world. They are already ruling most of the technology companies, but they will rule the entire world, and they will be omnipresent in every country and every company which uses the technology. And particularly in this AI era, this is much more important. So all of us collectively work towards this goal. And I thank the organizers giving me to share some of my thoughts today to all of you. My only appeal is not only just teach these new technologies, let us change collectively the narrative which we have that only some selected elite institutions are the cause. There are a lot of talent in our rural part of India, and many of these young people can contribute if they're given an opportunity, and this opportunity should be provided through these kind of platforms, and which today we are able to run these all online with the blended learning. So that's one possibility. I think these technologies are there for the betterment of the mankind. So I wish you all an enriching and inspiring learning experience in this course. I thank once again for giving me this opportunity. Namaskar, Jai Hind, Jai Bharat.
Thank you. Thank you so much, sir, for your kind words and great vision with which this curriculum has been designed. I would now like to request Dr. JBB Reddy, Head of Quantum Technology Cell, Department of Science and Technology, Government of India. Sir has been a great visionary and the man behind this course being organized here, and also the curriculum that has come up. And sir has been part of various initiatives, especially the futuristic technologies, smart grid, and also the quantum mission now. I would request Dr. JBB Reddy to share his views.
Thank you very much. Very good afternoon, everyone, and warm greetings from the Department of Science and Technology. First of all, I would like to thank AICT Academic at MNIT Jaipur, IIT Guwahati, IIT Roorkee, and IIT DM Jabalpur, NIT Patna, and IBM and AICT for organizing this faculty development program on quantum computing. India's National Quantum Mission is a visionary initiative uniquely designed to harness the potential quantum. I would like to highlight that one of the priorities of the NQM is human resource development and capacity building. And in this direction, DST under the NQM has taken several proactive efforts. In record time, DST and AICTE under the National Quantum Mission have launched the world's first national-wide undergraduate quantum minor program. This groundbreaking course will roll out at least 100 AICTE affiliated institutes by August 2025. Now it is less than 6 months away. In this short time frame, our goal is to train hundreds of faculty members to effectively teach this program, positioning India as a global talent hub in quantum technologies. Through the NQM, we are committed to making India the world's leading source of quantum talent. We want our students to be the best in the world, equipped with cutting-edge knowledge and skills. I extend my sincere gratitude to AICT, MNIT, and other partnering institutes for complementing the efforts in human resource development in quantum computing domain by organizing this national scale faculty development program. With expected participation of over 500 faculty members, PhD students, and professionals, this initiative is a remarkable step toward building critical human resource required for quantum ready India. Now, I would like to share a small PPT presentation to highlight the national quantum activities. I hope are you able to see my screen?
Yes, sir. Yes, sir. We are able to see.
Okay, thank you very much. Yeah, quantum technology is one of the 9 missions of the national importance. Sorry. This mission is driven by the Prime Minister's Science, Technology, Innovation Advisory Council. This mission intends to leverage cutting-edge scientific research. Department of Science and Technology is implementing this mission along with the other key ministries. Yeah, quantum technologies have critical application potential in several sectors. For instance, in communication sector, it can be improve data security. In health sector, it can enable less invasive, more accurate diagnostics and considerably increase speed of drug discovery. In financial sector, it can enhance the security of transactions, increase the speed of data analysis and financial forecasting. NQM has 4 verticals: quantum computing, communication, sensing and metrology, materials and devices. Specific deliverables have been identified for each vertical. For instance, under quantum computing, target has been set to develop quantum computers with 1000 physical qubits, and under quantum communication, target has been set to develop secure quantum communication, both satellite and fiber-based networks. And also, NQM has a clear strategic roadmap for the 3 phases. In phase 1, we are focusing on prototype development. In phase 2, product development and deployment. And phase 3, business development and economic growth. NQM has established 4 thematic hubs. These 3 hubs will coordinate with the technical groups for innovating future innovation. And these 3 hubs are Section 8 companies. These 3 hubs are responsible for technology development, capacity building, supporting startup, industry partnership, and international collaboration. I would like to give the glance of the 4 thematic hubs and technical groups. Computing hub has been established at IISc Bangalore, coordinating with 4 technical groups. Communication hub at IIT Madras in association with CDOT, coordinating with 5 technical groups. And Sensing and Metrology hub at IIT Bombay, coordinating with 2 technical groups. Materials and Devices hub established at IIT Delhi, coordinating with 3 technical groups. These 3 hubs were formally launched on 30th September 2024. These 4 T hubs brought in about 150 researchers from 43 institutions across India. Now, this India DST is keen to facilitate the growth of startup ecosystem and make them an active part of technology delivery. T-Hubs will create a national facilities which will be open to startups, and also T-Hubs will provide technology and business mentoring and equity support. NQM has developed exclusive guidelines for effectively onboarding and supporting startup, since quantum technology is a nascent stage and requires huge investment. In first phase, we supported 8 startups and launched on 26 November 2024. DST is intended to actively engage industry to enable technology transition through T-Hubs. Access to national facilities will be provided to industry stakeholders and co-develop technologies and will develop a revenue share model. DST initiated Quantum Awareness Program as a part of NQM among students, researchers, industry professionals, and policymakers. DST intend to build capacity and contribute to policy development. As a part of this initiative, DST along with AICTE developed a curriculum on quantum technologies for Biotech minor and launched on 24th December 2024. Efforts underway to initiate the course like book writing, video recording, faculty development programs. We are intent to provide financial assistance to technical institutions for setting up of the laboratories in quantum technologies. Thank you. Thank you very much.
Thank you so much for your valuable input, sir, and the grand plan for the National Quantum Mission and the various initiatives that are there for Indian researchers and faculties to take it forward. Thank you so much. I'm very delighted to inform that Professor Narayan Prasad Padi, Chairman EICT Academy, MNIT Jaipur, Chairman Board of Governors and Director, MNIT Jaipur, was able to join. Sir, very good afternoon. And this is the time for Professor Padi to share the ideas and the vision for quantum in MNIT Jaipur.
Am I audible, Dr. Pilli?
Yes, sir. Yes, sir.
Yes, sir. You're
Okay,
audible.
so very good afternoon, Professor Sitaraman. Wonderful meeting you again after today morning's interactions from AICT. Then we have actually Dr. JBB Reddy from DST and technical partner IBM partnership scientists and partners and all the respected delegates, dignitaries joining this inaugural event of FTB through AICT Academy on quantum. Now, strongly not only acknowledge but agree with Professor Sitaram Sanjay Reddy's view that how this mission is important as on today. Now, MNIT Jaipur as an institution, not only partnering with AICT Academy for training or capacity building, but we are keen to be partner to some of the leading industries and organizations like DST and AICT to make sure that this program, this training program is not only building the capacity, but also creating a wonderful ecosystem on quantum to benefit India and to truly visible, to make it visible to the world that India is not working on quantum, but also having a large capacity which can contribute to the global economy. Now, once again, I'm very, very happy to lead this initiative on behalf of the ICT Academy at MNIT Jaipur. I thank actually Professor Binis Saula and Dr. Pili for taking a wonderful lead and executing this program. And probably we'll have many phases of training program. I've been told that almost 800 plus participants are, taking benefit of this training program. And probably we request AICT as well as DST to make sure that to encourage other participants also to take part and take maximum benefit out of this program. Once again, I thank all my dear students and friends, those who are part of this event. Please take maximum benefit out of this program and see to that you contribute significantly to the national building. Jai Hind, Jai Bharat. Over to you, Billy.
Thank you. Thank you so much, sir. Thank you for your kind support and encouragement that Electronics and ICT Academy is able to make much progress. And at this time, we were about to have Mr. Sandeep Patel, General Manager, IBM India and South Asia, to be with us. Because of this technical issue, sir was not able to join. I would request Dr. L. Venkat Subramaniam, IBM Quantum India leader, to share his few words. Before Sir shares, I would request all the dignitaries to turn on their videos. We would like to take a photograph. If all of you are turned on their videos, we'll take a pic. Dr. Nivedita, Dr. Rajiv, Dr. Jagdish, Dr. Rajiv. Padi sir, once.
Yeah, am I audible?
Yes, sir. The video, sir.
Please.
Yeah, we'll take the pic. Yeah. Thank you. Thank you so much. So I will request Dr. L. Venkat Subramaniam. He's been the great push behind this program. He said that we'll have to do. I would also like to inform on the screen, you are able to see about 580 participants. But because of the same issue, many of them are on the YouTube link already, and many of them are watching the proceedings on YouTube. I would like to apologize to all the YouTube participants. We will shortly bring you all onto the main WebEx portal within some time once the inaugural is over. Thank you so much for joining. There are more participants otherwise elsewhere. So over to Venkat, sir.
Thank you. Thank you so much, sir. So today is National Science Day, and it's a great pleasure that on National Science Day, EICT, MNIT Jaipur, AICT, DST, and IBM are coming together to launch this big, training program for faculty. We have more than 600 faculty who have actually registered to take this course. And as you know, the previous speaker said, like Professor Pradhi, Professor Sitaram, Dr. JBV Reddy, this is, one of the first such programs across the world. Okay. Nowhere in the world has there been a program at a national scale to educate all the undergraduate students, giving them an opportunity to start a minor program in quantum technologies. This is only happening in India. And also, in IBM, for the past 3-4 years, we have seen over 2 lakh students from India actually registering on the IBM learning platform. 2 lakh students. Okay, can you imagine that? 2 lakh students, more than anywhere else in the world. And now, through this program, they are getting an opportunity to get a formal education in quantum technologies. And as the previous speakers mentioned, this is an opportunity for India now to take the lead by becoming the talent hub for the world and becoming the place where all the innovations in quantum technologies come out of. So thank you so much, MNIT Jaipur and EICT for starting this program with the help of AICT and DST, and we are very happy to support this. Thank you so much.
Thank you, Dr. Venkat, because it is your drive that it's not only one course that we want to offer, we'll go ahead with a series of courses. So this year will be fully occupied, and hopefully you will benefit, most of you will benefit from the entire overview of quantum through these courses that are lined up. I would like to also request some of our speakers who are here, resource persons will be sharing. Dr. Mustafizur Rahman, a few words from you. Then I will request Dr. Mani Madhukar to share the broad plan for this time. So over to you, Dr. Mustafizur.
Yeah, thanks a lot for inviting me in this speaker list. And I'm probably one of the youngest member here, so I have nothing much to say. But to me, it's a very big responsibility in terms of because some of us just recently completed our PhD and all, and just started this journey. And the technology as a whole, from starting with the hardware as well as implementing middleware software, as well as what is the industry requirement, what is the country's need. Suppose when the quantum computers are available, then what is the advantage of the quantum computer in real world? So we have to be get ready as a whole nation, and this is a very big responsibility for us. And I think we are at the right time with the right set of people and interested, like a lot of curious minds. So it's a big journey, and I hope we'll make it complete, we'll make it successful. And thanks a lot for like starting this initiative. Thanks.
Thank you so much, Dr. Mustafa Rahman. Dr. Mani Madhukar, also a very key person in bringing AICT, DST, IBM, MNIT Jaipur, and EACT academies together. So it's a joy, and he's been a great friend and supporter for us. So I will give this time for Dr. Mani Madhukar to share.
Thank you, sir. And it's really been an honor and pleasure, to be associated with this, right? And and fortunately, it was such a collaboration which everybody came together on this platform, right from AICTE, DST, EICT academies. They have been, really they have come together to sort of make this happen. So I think it's a great platform for all the faculty members to come be a part of it in this capacity building initiative, because as you all know, quantum is really going to be coming in a big way, right? And we can see the kind of impetus which enterprises are putting in quantum computing, right? And it's hence very important for academia also to ramp up the work that they have already been doing in terms of research, but then more towards enterprise adoption of quantum. And for that matter, it's really important that we have a good number of people, number of SMEs in the academia who can actually take this knowledge to their students, so that we are actually a quantum ready nation for that matter, right? India becomes a quantum ready nation as the honorary PM actually wants us to be. So this series is going to be, we are starting with the 7 FDP series for now, right? And the entire objective is to, get all the faculty members an avenue for learning the content in a structured manner as AICT has released the model curriculum, which has inputs from so many experts, right? So we are planning to have an entire series. In the first phase, we're going to do QT01, QT02, and QT03 enablement. Each of these FDP is like a 20 days, 40-hour program. We are trying to keep it at a common slot of 2 to 4 p.m. So we have tried to accommodate that everybody, is able to join this. And once we are done with the first 3 mandatory subjects, we are planning to have a physical contact program for people who can come to various EICT academies and other places, so that we can have a one-on-one with these people who are really keen on developing competencies in quantum computing. And MNIT has even bigger plans, right, which they are working on under the aegis of EICT academies. And towards the end of the year, we really want to look forward to having a good number of faculty members who are competent with quantum computing. And at the same time, will be able to offer, this program as a minor specialization to our undergraduate programs. And it can actually boost research in academia for that matter. So wishing everybody, a great luck, with this learning journey of yours, and good to be a part of it. Thank you. Thank you, sir.
Thank you, Dr. Mani. And it's time for Ms. Nivedita Dey, who's working with PricewaterhouseCoopers Quantum US R&D. I would like to inform you that today is 2025, but way back in 2021, again with the same IBM collaboration, Ms. Nivedita Dey led a full course on quantum computing. So 4 years later, I'm sure she is more more learned and more exposed to quantum computing, and hence we will look forward for a wonderful time of learning from her. Over to you, Ms. Nivedita.
Thank you, Professor Pilli. So again, am I audible? First of all, am I audible?
Yes, please
Okay.
go ahead.
Okay.
Yes.
So it's a big opportunity for again, like being invited, and it's a big honor to me personally. I had a huge respect for all the like IITs, NITs, MNIT, and all the professors of there. I know the power of academics. That is what we are like in industry, no matter where we are, but every time it's the like core knowledge that we get from academics that actually leads us in anywhere in the world. So with a huge respect, yes, there is a difference. When I was in 2021 and delivering the lecture for quantum, at that time I had mostly the knowledge of academics. Right now you can say that being in PwC, being in a like fast-paced environment, dealing with the investors, dealing with the stakeholders all the time, I understand that what is the business need for quantum, like a niche technology like quantum. So what are their expectations? And the perfectly identified picture is that, yes, we have a lack of resource even in 2025. And as an Indian, we all should work together for that. So I just hope that I can meet all the expectations, and whatever they just want, at least I can create a base so that they can jump into quantum and contribute significantly in this field. So yes, thank you.
Thank you. Thank you so much, Ms. Nivedita. She will be dealing for more than half of the course. And we have Dr. Ashwath Babu, who will be leading us on quantum sensing. He's faculty with IIIT Dharwad, but he did his PhD from IIT Kanpur. Sir, few words.
Hello, Dr. Pillai. Thank you very much for inviting. So, yeah, I would like to say a few things here. First of all, kudos to our Indian government, not just encouraging on the research front, also looking forward in developing the human resource. That is through AICTE minor. So that is something amazing. Like Dr. Venkat mentioned, it's not happening in any other country. So it's a unique way our Indian government is working from all the aspects, either from the research side or from the students educating in quantum side. So that is something amazing. So with this, I would like to thank MNIT for inviting me and Dr. Mani for roping me in for this FTP as a resource person, and Dr. Venkat being a mentor to me for the past couple of years. So he was one of the key lead in our mentoring team, which actually mentored a quantum minor in our institute at IIIT Dharwad. So we are in the second year for that minor program. So thank you very much, Dr. Venkat, for that. So having the experience of that 1 year of quantum minor, so I would try my very best to fulfill my responsibility given by this MNIT as a resource person for this FTP. Thank you very much. Once again, have a wonderful day to all the participants, and I hope you enjoy the entire FTP. Thank you, sir.
Thank you. Thank you. We have two chief investigators of Electronics and ICT Academy here. We have Professor Vineet Sahula, who is the chief investigator in MNIT Jaipur itself. Welcome, sir, and Professor Aparajita Oja, IIIT DM Jabalpur. A few words from each of you, please.
Madam, you please first. Please.
Okay. Professor Aparajita Oja.
It's great beginning, I must say. The chairman, Professor Sitaram from AICT, DST, Professor Dr. Reddy, and then I can see my friends, Dr. Pilli, Professor Saula, and Mani Madhukarji, Namitaji, and my colleague Deep Prakash, who has also been teaching quantum technology here at IIIT DM Jabalpur. So I can only say it's a great initiative and we are lucky to be part of it. We hope that we will live up to the expectations of all the participants because we have great speakers here. So on behalf of the Academy, EICT Academy family, we welcome you participants. That's all I want to say. And I must thank Dr. Pilli and Professor Saula for taking up this initiative of continuing. This is only the first in the series. We are going to host many more such programs. Thank you so very much, all of you.
Thank you, ma'am.
Thank you very much, madam. Thank you, Dr. I think I will just cut short and thank definitely Mr. Mani Madhukar, who has initiated this kind of an idea, which we never knew we could actually have a concrete shape so early and so quickly. Thanks to him. Thanks to Dr. Pilli. He's working, I think, more than 24 hours a day for last 15-20 days. And this program has taken shape. And I would also like to acknowledge Professor Padi, our director, sir. He keeps a very soft ear to our ideas, even if they're not very well cooked up. And with his continuous support for last 20 days, this program has actually taken shape. I am just incidentally here. The credit goes to Professor Dr. Mani Madhukar and Pilli, who have just planned this. And also thanks to Professor Sitaraman Saab and Dr. J.V. Reddy Saab, who has actually supported this kind of activity right from the beginning, assuring us that this program will actually take shape and go along with some kind of a series in 6 programs there. And thanks to all participants, and of course, all my chief investigator colleagues across the NITs who could see the things coming up and join this program very willingly and let us take ahead the kind of things. And we are happy as an institute to complement the government effort and prove the value of such programs which is funded by Ministry of Electronics. Thank you very much.
I'm extremely sorry here. I missed Professor Srihari Rao Patri, who had joined from NIT Warangal. Sir is also one of the chief investigators of the Electronic ICT Academy in NIT Warangal. Sir, few words, and we'll conclude after that. Yeah.
Thank you very much, sir. Good afternoon, all the respected dignitaries, Professor Sahula ji, and then Professor Pilli ji, and then all other Academy chief investigators, and all the dignitaries from the IBM and all other speakers, and Professor Sitaram ji and all. And I congratulate Professor Sahula ji and then Professor Pilli ji for just now coining the FDP. This is not just only FDP. long journey, and I think the way in which it is no scheduled and all, really it seems to be the first of its kind, and then it not only takes forward the objectives of the Indian City Academy, but also rather it expands its wings towards fulfilling the government of India's vision and mission. And I congratulate all the participants for showing their interest. And then please remember that all the my dear participants, this is the beginning of the journey. Please have patience, and then continue the journey till end of all the series of the courses, so that the maximum benefit is derived out of it. Thank you very much once again. And with this, I wish all the best for the series of the courses. Thank you.
Thank you. Thank you very much, sir. Before Dr. Mahipal Jadeja gives the vote of thanks, I just want to add a few things me and Professor Badi were discussing. And AICT and DST came together with IBM and CDAC, and the curriculum has come forward. EICT academies and the Ministry of Electronics and Information Technology have come together with IBM, and then we have brought in a series of faculty development programs. Now, various faculty members from various universities and AICT affiliated engineering colleges are attending this program, and they will learn and they are exposed to many new technologies. They will share with their students. So all the participants who are here, my request, my sincere request is that whatever we are learning here, we are going to share it to the students. That is the vision of Electronics and ICT Academy. The vision is to train faculty so that they will share the wisdom with their students who will become better employed. And one of the thoughts that Professor Padi sir was sharing is a few students actually get so excited about quantum, and they will start working on some research problem or some idea, and hopefully someday we were looking at many new quantum processors released in 2024, November, December, and January, February. Amazon came up with its own processor yesterday, 2025, February 27th. You can look up the internet, and in December, Google came up, in Microsoft came up in January. IBM had its own improved version coming up in November 2024. So with this, we are hoping that whatever we are going to share here, in line with Dr. J.B.B. Reddy sir's vision for the National Computing Mission, I would say someday we may have a Make in India quantum processor coming up from among one of our students. I think that's going to be the great impact of this program. Hopefully, I'm hoping that this is what is going to lead. So the responsibility is being transferred from our side to the faculty members who have joined here. About 500 are there here. Many are there on the YouTube. So we hope that this will really impact our country, and someday we will make our nation proud. Thank you so much. Over to Dr. Mahipal Jadeja. He will share the vote of thanks.
Good afternoon to all. It is my privilege to extend a heartfelt vote of thanks on behalf of the organizing team. First and foremost, I express my sincere gratitude to Professor T.G. Sitharam, Chairman AICT, for his insightful remarks on the minor UG curriculum on quantum computing. His guidance in shaping academic knowledge for emerging technologies is truly valuable. I extend my appreciation to Dr. J.B.B. Reddy, Head Quantum Technology Cell, BST, for enlightening us about the National Quantum Mission and its significant role in advancing quantum technologies in India. A special thanks to L. Venkat Subramaniam, IBM Quantum India leader, for sharing valuable industry perspectives and support for quantum technology initiatives. I am also deeply grateful to Professor N.P. Padi, Chairman E&ICT Academy, Chairman BOG, and Director MNIT Jaipur for his exceptional leadership. His dedication to advancing academic and research excellence at MNIT Jaipur is truly inspiring. I also extend my sincere thanks to him for encouraging industry interactions and collaborations like this, which bridge the gap between academia and real-world applications. I would like to express my gratitude to Dr. Namita Mittal, Head of CSE MNIT Jaipur, for her constant support and encouragement in creating an enriching academic environment. My sincere thanks to our esteemed resource persons, Dr. L. Venkat Subramaniam, IBM Quantum India leader, Dr. Mustafizul Rahman, research scientist, IBM Quantum, Dr. Mani Madhukar, program lead, IBM IC, Ms. Nivedita Day, PwC Quantum US R&D, Dr. Aswath Babu, assistant professor, IIIT Dharwad. Their expertise and contributions will undoubtedly add great value to this program. I also extend my gratitude to the chief investigators of AICT academies for their pivotal roles. Professor Gaurav Trivedi from IIT Guwahati, Professor Sanjeev Manhas, IIT Roorkee, Professor Vinit Chawla from MNIT Jaipur, Professor Aparijita Oja, IIT DM Jabalpur, Professor MP Singh, NIT Patna, Professor Sri Hari Rao Patil, NIT Warangal. Their dedication and efforts will be instrumental in ensuring the success of this initiative. Lastly, I extend my heartfelt appreciation to Dr. Pilli, Principal Coordinator QTA at MNIT Jaipur, for his continuous efforts in organizing this program and ensuring its smooth execution. And also, I would like to include other joint principal coordinators like me, including Dr. Rajiv Arya from NIT Patna and Dr. D. Prakash Samajdar from IIIT DM Jabalpur. Lastly, I would also like to add Mr. Dipesh and Mr. Parmeshwarji for technical support. With that, I once again thank all the distinguished guests, participants, and organizing members for their valuable time and support. Thank you.
Thank you so much, Dr. Maipal Jadeja. And thank you all the esteemed guests who have joined. And thank you so much for joining with us. And maybe just after a brief moment of time, we will start with the first lecture on 4 verticals on quantum technologies by Ms. Nivedita Dey. Yeah, if there's anything anybody would like to add, it's time for the panelists. Thank you. Thank you so much.
Thank you, sir.
Yeah, so I think, thank you so much. We will move to the lecture now. We are late, sorry for that. But we will have Dr. Nivedita, Ms. Nivedita to start the lecture. Over to you, ma'am.
Yes, sure. So, good afternoon, everyone. Let me share my screen. Okay. Okay, I'm sharing the screen. This one, yes. So again, a warm welcome to all the participants. Thank you for giving time and trusting me for the first session. So today, now all of us know that we have to do quantum, but the thing is that how to do it, we do not really know, or the that pathway we do not have yet. So for that, what I have thought is, since this is the ice-breaking session for quantum, so maybe we can follow a good standard, which is a standard way of learning anything, not only quantum. That is, we will understand the ground, that is why quantum is actually needed. Then followed by, we will slowly, as and when we actually go into the further classes, so that we can understand everything related to okay. Sure. Let me do that. Yeah, thank you. Yes. So so that is the target. So hoping that in mind, let me start. And meanwhile, if you have any doubt, you can like very serious doubt, you can ask me at the like unmuting yourself and ask me intermediately, like whenever you want to. That is, there is an issue with the audio, or you cannot see the screen. There is issue with the maybe the PPT or the slide is stuck somewhere. So all these kind of technical issues. And if you have some questions that you want to discuss, so you can put it on chat, or maybe at the end, whenever we'll be discussing it, we can discuss it. Okay, so with that kind of like enthusiasm, let us start. So yes, first thing is, why do we need something new? Concept is, so I will be highlighting a few scenarios, kind of stories, a few stories, so that we can understand that is there any challenge, or is there any need, or is there anywhere where our classical systems actually they fail, or they are not at par, they cannot meet the expectations as we are expecting in the real world? Is there any certain scenarios or situations? So first we will be analyzing a certain situations. So let me start with the logistic company. Okay, so what their target is, a very good optimization problem they have to solve like on an everyday basis, that is with the fleet optimization or supply chain optimization or route optimization. All these things are part of the logistics field. So where their target is the optimization, where you have to like maximize the efficiency, maximize the reliability, or minimize the cost, or minimize or find the best optimal route. Now we all know, for example, say traveling salesman problem, which is there for the route optimization. It's a very well-known problem, or called TSP, where a traveler had to actually travel a lot many cities through a Ham cycle or Hamiltonian cycle, which is you have to actually traverse to every node exactly once, but you have to come back to the original node, and the condition is that all the nodes should be covered. So that is a Hamiltonian cycle. So that is the problem of traveling salesman problem. Now this is a mathematical problem, TSP, but it is very much used in a lot of optimization problem. But very like obviously we can think of a route optimization or route optimization problem. So what happens is, even if you apply a very good optimization algorithm on classical, which is, for example, say, which is also optimal and it's reliable. So say, for example, it's a dynamic programming approach that you are applying, where it uses a couple of like a memorization technique, where a certain problems, once you have the answers, you actually store it, so that whenever the next, say at after some time, whenever the problem size gets bigger, you don't really need to solve it from the scratch. The basic idea, fundamental idea is that, so that you can reuse the obtained values from past. That is a basic thing. But even if you do that, you can only get benefits for those problems where like the things are repeating. That is, a certain value, you can again reuse it. But in case of TSP, or in case of certain problems, let us now only consider the example of TSP. You actually cannot do that. Why? Because whenever you are exploring the entire search space, that is, you are exploring all possible ways that you can follow in order to get the based route, you will see that there are very less number of repeating cases. That is, every path, or that entire path is very unique. Now, say for example, you have 100 such cities that you have to cover. In real life, though, it can be even more than that. If it is 100 cities, then it is basically like, say, 1, 2, 3, 4, 5, 6 till 100 is a possible way. Now you can make it like 2, 1, then 3 to 100 in the sequence is a possible way. Likewise, every possible ways can be there, where the repeating cases are very less. Now you understand that all optimization problems are really not very easy, or not somewhere where you can actually use a certain value. You can use value. For example, it's a factorial problem. Okay, you want to calculate the factorial 5, which all we actually draw the stack and the memory, what is the memory, everything. So if you want to calculate the factorial of 5, what you can do, you can actually make the factorial 4. If you store some certain in a certain memory, you can store the value of factorial 4, then you can actually reuse it while calculating the factorial 5. But for these particular scenarios where TSP, or there are other also like complex optimization problems, you cannot actually do that. And the complex optimization problems in technical terms, they are called NP hard problems and NP complete problems. So you cannot do any betterment in those problems, other than some like some, say for example, some proximate solutions you are targeting for, or certain kind of relaxation rules you are applying, that okay, we will be like putting a certain constraint so that your problem size gets smaller, or it gets under less constraints. So just understand it, nothing quantum I am starting. So there are a certain scenarios where you will be facing issues. Why issues? Because it's not really the theoretically or the prototype level where you have only 4 or 5 cities, or a graph that we generally follow while giving example of like all the algorithms and all, that it's like a say for example it's 4, say for example it's 6, but in real life it can be very, very bigger than that, right? So for those things it is very challenging. So this is a problem where for NP-hard problems, the classical systems might fail. Why might? Because if we use HPC and that kind of logic, it might be a bit better, but even at least you have understood that there is a scope. There is a scope for alternate computing, or there is a scope for thinking it in a different way. This is the first thing. And why this happens? Just check the slide now. It's a combinatorial explosion of possibilities that makes it infeasible to calculate the best route with a reasonable time. Focus on the reasonable word, that you have to do it in the real time, in the reasonable time. And also, the another factor here is the dynamicity of the variables. It is so dynamic, the traffic conditions, the weather conditions, the geopolitical disruptions, and all those things, they can actually make it in real time, your optimization problem, very difficult. And also there can be other factors that might add on in between. So you have to keep a place for all those kind of variables to simulate the real picture. The first thing. So this is an example of a logistics sector. Now, say for example, another story, which is a pharma industry. Now, say for example, you want to simulate a drug. You want to simulate a drug, which is basically a protein, or protein is basically a polypeptide chain of amino acids and all those things we know. But the thing is that there are so many factors that if you just say, for example, in between two amino acids, if you change the angle, that kind of performance, it will be a new drug. So there are in a minute level, there are so many things that in order to simulate it in real time, it is going to take a lot of time. And if you increase one particular molecule into it, or say one amino acid, if you want to change any part of it in that kind of an hydrocarbon, if you want to change anywhere of it, it will actually increase your complexity even more, because it will be not an additive one, it's even an exponentially multiplicative one, kind of that. Okay, because it can be put in anywhere. It now that has a alpha, beta, and all those kind of positions. I'm not very well aware of the chemistry part, but there are a lot of positions of hydrocarbons which actually determine that what will be the phase, what will be the strength of the hydrocarbon, its performance, and all those things. So likewise, there is a challenge, because again, it's a lot many parameters, and simulating it in real time, it can actually take up like say 10,000 or a lot of time units in whatever format, which is again not in the reasonable time period. Okay. Now, another one is, say, for example, financial risk analysis, which is a Monte Carlo challenge. Again, same thing. So risk analysis, portfolio optimization, they also need millions of simulations in order to predict the stock behavior. And even after that, that can be wrong. So I'm not guaranteeing that if you have a quantum computer, you can have a great return or ROI from stock, but still it's a big challenge, because the challenge here is again the dynamicity and the lot many parameters which are changing in real time, the behavior of the all the like stakeholders, everything. So again, for these kind of scenarios, it's challenge. Okay. So the next one is a traffic flow optimization. Again, here your car movements can be in millions of numbers. Your traffic signals, they can have a real time impact based on and off, and all those possibilities in a multiplied fashion, on and off, into on and off, into on and off. Likewise, there can be weather, there can be accidents, there can be emergency route changes. So your classical systems, they are actually they literally fail when you have a certain kind of a deterministic approach. When you have a predefined rule, it can work. But when you do not have a predefined rule that is exactly from a particular state, on having a particular input, I have to go to, say, this particular place. That is my, on having A, from being B, I can go to C. When your C is fixed, classical can solve it. But whenever your options are, I can go to C or D or E, say have a three possibilities, then your classical system will fail, because the non-determinism, or where there is a possibilities of outcome or possibilities of choices, your classical system is really, you cannot logic it in that way through a classical machine or a classical algorithm. So what is the struggle with the classical computing in a nutshell? So why do classical computers struggle with these probabilities or these kind of problems? It is a combinatorial explosion. just remember the traffic flow or the like route optimization or the supply chain optimization, wherever you are using the TSP, say traveling salesman problem, you have a combinatorial explosion of possibilities. And the non-deterministic problems, I just right now mentioned it because many real world problems do not have a deterministic solutions. In decision making, at least you can remember, so instead they need a probabilistic model, and which our classical system is really not. It's a purely deterministic model of computing. It's not a probabilistic model. It cannot handle that one. Third one is the parallelism limitations. So even the best supercomputers still process in a fundamentally sequential manner. Because see, if your machine can be parallel, but then also even with that, there are a lot of like signal, the communication overhead, a lot of stuff. So the logic is you have to define it in a way so that whatever is the way you encode it through a parallel computers, ultimately you can retrieve the result. So it's a purely sequential logic that you develop, but it run through a parallel computers where your hardwares are multiple, or your CPUs, say for example, they are more in number, not the one. They are multiple in number. Your machines are more. So, what is the backbone of the classical machine that we work? We all know it's a Turing machine. So I do not know the participants whether they're from this like core computer science or electronics or electrical. So I'll not go into the depth of like that unrestricted grammars and the CFGs and all those things. But it's basically, you can think it of like whatever be the grammar or the rule through which a classical computer can work, Turing machine is the one that can work in that way. So it's a purely unrestricted grammar where from anything you can go to anywhere. Likewise, it's a logic. Again, I'm not going into the depth of technical for this thing. But you can think it of like the key characteristics of a Turing machine as it uses a finite set of states. Again, it uses a finite set of states. It reads and writes symbol on an infinite step, and it moves either left or right based on transition rule. That is, I am on state Q, I have a 0, so I will move to left. Or I am on state Q, I have a 1, so I will move to right. Likewise, you can define your logic, then your Turing machine will work. And why it is important? Turing machine model is the foundation of all the modern classical computers. That is a theoretical computer science. Basically, the way it works, it's basically a Turing machine. There are a lot of variants of Turing machine, but ultimately it's a Turing machine. So it shows that any computational problem solvable by an algorithm can be performed using a system that follows the principles of Turing machine. So again, it has a tape, which is a long infinite strip divided into squares of say 0, 1 and blank. It has a read-write head or say a pointer kind of thing. It has a finite control unit, which is a predefined rules or set of say transition functions or rules that determines that what the machine will do in the immediate next step. Likewise, based on definitely two factors: what is my current state, that is what is my queue, and what I'm reading. So what is the 0, whether I'm reading 0 or 1 or blank. Likewise, so I need two inputs, then Turing machine is able to predict that what is going to be my next output. Okay. The same thing is written over here. So if a machine is in state A and reads 0, it replaces it with 1, that is the action, and moves right. That is the head moves right. And if it is in state B and reads 1, it replaces it with a 0 and moves left, and it repeats until the halting condition is met. So these are the examples on what are the actions that are generally followed on a Turing machine, which is a classical model of computation. So again, so they are built on the principles of Turing machine, but with certain modifications. That is, instead of a tape, you can think it of a RAM or memory. It read-write head, they use a CPU. The transition rules are basically the key properties of the classical computers. So, but they follow the Turing computing model. So what is a model? The three things. First is the deterministic one. Given an input, and reading a particular say given an input being a particular state, it can always produce the one exact output. There is no choices that it either I can go to left or I can go to right. That is the choice, but you cannot simultaneously be choosing to go for a left and a right. That is not possible. That is a determinism. Second one is a step-by-step execution. That is, operations follow a fixed logical sequence. And a binary representation, you all know that it's ultimately in form of a zeros and ones. But there are certain limitations. The limitations is time complexity and space complexity. You all know what is the formal definition of it, that some problems require exponential time to solve. This is not a definition of time complexity. Time complexity means the amount of time taken by a particular algorithm to solve a problem, and space complexity is the amount of space required in terms of like memory in order to solve a particular problem. But it is that, but time complexity is a factor, which is a limitation for classical computing through Turing machine. That is what, for NP-hard or for a certain complex problems, it is an exponential time technique. And space complexity also, it can take an unrealistic amount of memory. Just imagine the situation of a, say, protein folding problem, where every amino acid or all the possibilities you want to encode. So that also is so huge that that is also a challenge for a classical one through Turing machine. And last 2 points are very interesting. Yeah, is motivation behind this? Oh, sorry. Can you just unmute yourself and ask the question once? Someone asks just a question now on chat. So can you unmute yourself and can ask the question?
Not everyone is able to unmute because of this large meeting, options.
Okay, okay, okay.
So, if
Okay, okay. Slide are not visible.
no,
No
they are
audio.
visible.
Okay,
No,
okay.
both slide is visible. We are also having audio. I will write it
Okay,
here.
okay, okay, okay. Those who are having any issue, please just leave the webinar once and then try to rejoin. I think that will solve. Yes. So, okay, let us just discuss it on the Q&A. We will be having a lot of discussions, no issues. So, third and fourth point are very interesting. That is irreversibility and energy loss. That is every step we do basically loses some energy due to certain principle. What is the principle is not very important, but it loses its energy. What do you mean by it? Irreversibility is basically a fundamental kind of limitations of classical one. I'm giving you an explanation to say very easy example. Consider the case of an AND gate. You all know AND gate. What is it? We all know it through the binary gate. It's a binary logic gate. It basically performs when both the inputs are one, it only produces a one. And in all other combinations with two inputs, either it's 0, 0, or it's 0, 1, or it's 1, 0, it will produce a 0 or off. That is a logic. Now just think you have only the output 0. You want to predict what will be my input, what was my original input. Can you do it? You cannot do it. Why? Because it could be either 0, 0, it could be 0, 1, it could be 1, 0. So whenever from output you want to identify what was my input, it is very challenging for classical gates. There are a certain gates which are, say, reversible. Say, for example, a NOT gate. If you have an output 0, you can tell that my input was 1. If you have an output 1, you can tell, okay, my input was 0. But for certain gates like AND gate, OR gate, okay, if you have an output, say 1, can you tell me the input was 0, 1, or it was, say, 1, 0, or it was 1, 1? You cannot tell me. So there are certain classical gates or the, say, Boolean algebra logic, classical logic, which are the fundamental to build a classical one, like classical hardware or classical computer. They are built on the same logic gates, and those logic gates irreversible. And every time you perform a step, you lose some energy. What do you mean by energy? Energy is nothing but you can think it of an information. Some information will be lost. As in when you perform an operation, some certain amount of information that is a meaningful data which you should have, that is being lost into the system somewhere. You do not have any access to it. So this is a big problem that classical systems have. Or remember all the points that we are going to actually try to have a better solution. Okay, so irreversibility is a big problem. As and when we perform a particular step, some fundamental level of energy, which is nothing but some information, which is nothing but some meaningful data, that is lost. So you cannot track actually to the where you have started. You cannot track it back. Okay, so that is a challenge. And the fourth one is your inability to model a quantum systems, because classical bits fail to represent quantum states accurately. Quantum states is a big thing. We will be actually talking about it. As of now, just remember it in this way. Say, for example, some particle is there which you do not have an idea of how it behaves. So it's in a quantum world. You do not have that idea. It's so like microscopic or nanoscopic level that you cannot really understand or predict or capture or like manipulate anything you say, its behavior. For that, why? Because you are in the macroscopic level. You are in the macroscopic world. So this transition is very difficult for a classical bit or a classical logic to devise if you want to predict a quantum state, a state which is not under your control, where you cannot directly move into it. Okay. So if you want to do any manipulation or any alteration, or you want to just identify its behavior, predict, measure, anything you say, you cannot do it through the classical computers. So your inability to model the systems which is not under your control, let us say quantum with this keyword, that not under your control. So your inability to model not under your controlled systems, you cannot do with the classical logic. Great. Now the thing is that, okay, so some problems require exponential time to solve, just like certain for all the 4 points I just mentioned. Let us go a bit more with a certain example so that we understand it better. So time complexity, some problems require exponential time to solve. Like many real world problems, say for example, a cryptographic key breaking. Okay, so where you have a say 2048-bit RSA key. RSA is a cryptographic algorithm, which is a public key algorithm. We will be all discussing in a very detailed way about these things in quantum cryptography and communications, even in QT01, I guess. So we will be all talking about it. But if you have a like very strong cryptographic algorithm, which we believe right now is a very strong thing, with a lot many sizes of keys, say for example, RSA 2048-bit key, or say ECDSA, all those kind of elliptic curve algorithms or digital signature algorithms. So those asymmetric algorithms, mostly asymmetric, where you use actually private key and a public key, all those things, they are very much time taking to break. That is why we are using it, so that it doesn't got actually leaked, or any of our confidential information, they are not leaked. That is our purpose. So that's why we are using relying on those kind of key. We are not hackers, but for even for the hackers, or even for certain simulating the brute force or the like differential cryptanalytic attacks, mostly it's very difficult. You cannot do it in real time. So, and for large scale optimization, where like CTSP with 1,000 city, 10,000 city, 1 lakh number of cities, so they fall into the category of say complex problems or into hard problems, which require exponential time for classical computing. So example of the bottlenecks are say factorization of large number. Why I'm choosing the factorization of large number? Because it is the fundamental say math logic for any of the cryptographic algorithm. Mostly, or the half of the cryptographic algorithm family. So it is basically the factorization of a very large number. You have, say, for example, 100-digit or say 1 lakh digit long product, and you want to find what are the two factors that actually made up that product. And you want it in an easy way. Say, for example, you have 60, 60, and you what? Can you tell me that what was the two factors that made it up? Say, for example, one was the private key, one was the public key, and 60 is the product. So I'm giving you only 60. If I would be giving you 12 and 5, you could directly tell me that, okay, the answer is 60. It's very easy. It's just a product. Multiply both the numbers, you will be getting it. But if I give you 60, can you again give me what was the original two factors? You cannot. Even if you can and test with all the possible cases, you can only do that because the number itself is very small. It's only 60. But if I give you 6 million, say for example, okay, the number itself is 6 million, say, okay, and 6 into 10 to the power 6. And if I want you to tell me that, okay, in one shot, or say a reasonable number of shots, just tell me what was
Yeah, suddenly it seems she's disconnected. Rosapilli, can you please find out? Yeah, wait, participants, wait for a while.
Am I audible?
Nivedita ji, yeah, now we lost your voice in between. You are audible now, yeah.
Okay. Okay.
For a couple of,
Okay.
yeah,
Yes.
minutes, seconds, yeah.
Okay.
Please go ahead.
Okay. Yes. What I was just telling. Yeah. So factorization of large numbers I was discussing. So it's very fundamental. And if I give you like say 6 million, so you cannot tell me in real time what was the two factors. And the similar logic was something that came in the mind of Rivest and Adelman, who are the pioneer for our area. Their names only you can have the algorithm RSA. This similar thing came to their mind. So let out this logic and for algorithm. So these things, all the public key cryptographic algorithms are built. So this is a problem where we cannot do it. So the classical algorithms fail in this field. And next is a TSP problem. Now you all know about it, that brute force in a classical solution, it is very impractical to increase the number of cities. It's basically, even with the dynamic programming, it's n square into 2 to the power, and we know wherever like n is an exponent, it becomes, that complexity is very, very much big, okay? It is exponential basically. Even space complexity for T, that also is n into 2 to the power n. So, and since you have n cities, so it's basically n into 2 to the power n. Likewise, it's n square into 2 to the power n.
So Nivedita ji, your voice is breaking again and again. Hello, Nivedita.
Beyond
Your voice is breaking again and again, Nivedita ji. Can you please check the signal at your end?
Okay. Just a minute. The same problem I'm facing also today morning. Start once. Okay, let me start sharing because I've joined with mobile data, so maybe it can be a certain problematic. Just
Okay.
waiting for it.
Yes.
Okay, yes. It's connected. It should be connected at this time. So, yes. So the second one was space complexity, the memory bottleneck, relations and all those things. Just told you that if you want to put it in the search space, it will be taking a lot of
I'm
space in
sorry
the
again your voice is breaking and we cannot see your screen as well.
Okay, I think just some minutes.
Yeah,
Can also
there's
put
some.
as pause. Just a minute.
Yeah, we are also waiting for Nivedita ji to join again. She is having some problem, perhaps. So participants wait for a while, like they are doing something. Yeah.
Okay. Am I audible now?
Yes, you are audible.
Okay. Yeah. Yes, the internet issue is finally okay now. I can also share my screen.
Yeah.
Yeah. Okay, please. Just a minute. Yeah, I guess spaced out. Very sorry, everyone, for this thing. From today morning, I'm facing this problem. Extremely sorry. Okay. So, hoping that we are all again back with everything. And I guess all of you also have got 5 minutes of break. Yes, definitely, I will be sharing. Okay. So, mm, so the protein folding simulation, wherever there is a space issue and the high dimensional data processing. Consider the AI case where we generally do the principal component analysis and all those stuff. So whenever there are a lot many parameters or say columns of data that we want to evaluate, that we want to process, that we want to mine, all for all those cases, it is also very challenging because those many parameters we directly cannot fit into, even in simulation for AI, for all those problems. So what we do is we actually very strategically try to just put a particular optimization or try to minimize the way it was. So in that way, we perform a certain kind of information loss. So it can be biased or it has a chances of a biased decision making if we do that. So if we have say 50 lakhs of parameters for our feasibility, what we do is we actually use a very minimal number of parameters. So we actually do this kind of fine tuning. But what happens is for all those fine tunings, since you are using some random logic through a classical machine, it can happen. Yeah, I'm doing it in the slideshow mode. So what will happen is you can actually lead to certain kind of inefficient system or inefficient decision making, and that has a huge impact for real businesses. And then simulating a many body quantum system, just have told you. So anything that is a quantum, you cannot really simulate with a classical one. That is part of quantum simulation. Okay. And memory needs for a classical versus a quantum simulation of molecules, you can actually define. These two are the examples, the last 2 points, an exponential growth of required memory for classical versus quantum system. Next was the irreversibility. So the Landor's principle, what it says is erasing a single bit of information dissipates at least K into T into Ln2 amount of energy, where K is the Boltzmann constant and T is the temperature. And we have right now know that, yes, what we are talking about, how the irreversibility and the lack of way to proceed from the current one to the previous one can lead to an information leak. So every step here matters. Every step will lead to a certain amount of energy or the data, meaningful data, or the information dissipation. Second is a heat dissipation in modern CPUs, as and when the transistors, they are basically shrinking. So heat generation also increases, leading to the limits in the processor speeds. Okay. And cooling cost for supercomputers. High performance classical systems require a massive cooling infrastructure. So they are very unsustainable for the future computing needs. Okay. And so, yeah, again. And inability to model a quantum system is the exponential growth of the computational cost that cannot do the chemical and the material simulations. Accurate modeling is not possible. And cryptography and security, of course, the classical encryption model, they do not naturally capture the quantum randomness. This line means a lot. We will discuss it again in detail. Just understand one thing: no deterministic logic can be truly random. Just remember this one line, that is, if something is deterministic, it cannot be random. Why nature is random? Because nature is non-deterministic. You cannot determine what will happen. When what will happen, you cannot predict. Okay, so or basically you cannot predict the outcome. But in nature, everything is there, but you cannot predict what will be the exact outcome, despite of several challenges. So that is a kind of a non-deterministic one, or the exactly perfectly random one, or a system with the highest amount of entropy. Entropy means a randomness. You cannot do that. So making them vulnerable to quantum attacks. Okay. So now we have understood. Okay. So this many time we have actually put on understanding the base, the ground, that okay, the classical, whatever we have known, we are doing with the DBMS, classical DBMS OS, like algorithms, everything, they are really based on a classical machine, and the Boolean algebra, everything that the logic gates, all the institutions, that whatever you are actually can see for the classical is basically not really suitable if we want to think of a particular scenarios or in particular situations. So we need something new. What is the new thing? During research, I guess a lot many years back, but when I actually started it, I found that it was a two kind of computing that deals with it, that can deal with these kind of problems. So one was a DNA computing, another one is quantum computing. So DNA computing, I do not have much knowledge of it, but it's basically just to give you a glimpse of what it is, both are non-deterministic models of computing, capable inherently, because it inherently is capable, that is automatically by itself is capable to process a non-deterministic logic. It behaves non-deterministically inherently. Okay. And DNA means, now we all know that the nitrogen bases that our like human body is made up of, okay, all those amino acids, proteins, they are basically ultimately the nitrogenous bases. So the A, T, G, and C for DNA, and A, T, I guess whatever uracil is there for RNA. So these computing models are basically the sequences. If you change the sequence, your entire like genetics will change. Those are part of the genetic. Whoever is working on that, they will understand. It's called a mutation or sudden change. It can happen. So it's a non-determinism. And researchers have found that okay, if we have to build a system which is can deal with the non-deterministic logic, we have to find those particles or those elements. We have to make our system with those particular elements in our hardware which are inherently non-deterministic themselves, so that they can process non-deterministic logic. And non-deterministic is power than the deterministic one. We already have seen that what are the challenges with the deterministic logic. You cannot really do everything simultaneously, even if we have a parallel one, because a parallel computer is there, but the logic itself is sequential. Okay. So what really gives this much of power to non-determinism is a certain things that we are going to discuss. Now, another one, just like the DNA computing, it's also very powerful, and a human brain is perfectly non-deterministic. Say right now, if I ask you that what you are thinking right now, you will tell me something. But if there could be, we could have a machine to just identify all of your current exactly at a particular instance, what are you thinking? It will never be at least one. It will always be like 10 or 15 or 50 thoughts might be there. It will be more than one, because our human brain, our mind is capable of thinking parallelly, simultaneously, several outcomes, several scenarios. But if I ask you, okay, one of the participants said, okay, what are you thinking? You will tell me that, okay, right now I'm just watching your superposition. I was just thinking that, okay, what we can do with quantum, but it's not true. But even if after that, if I ask you a question, you will tell me one thing, that, okay, this is the outcome, right? So measuring this thing is going to be different. The similar essence we are going to have in quantum as well. I will enter it. So just like this DNA computing, this kind of non-determinism, and whenever you are asking me a question, I will tell you exactly one output, though I am capable of thinking a lot many outputs simultaneously. This is a kind of you can say it's a class with these properties. Now, another dimension of computing came into picture, which was quantum after DNA. The researchers have observed that also in nature there is another thing, which is a photon, or say such kind of micro or nano level particles with specific features that they can be both in the waveform as well as in the particle form simultaneously. And they are capable of holding a lot many things together. But whenever you try to hit that particular particle, it will give you, okay, exactly one thing. So you can think it of a roll, like a say moving or rolling scaling property. Okay, I missed the question again. I will check it later. I'm not a one to tell about that. And then yes, so certain things are there. So whenever I think of it as a rolling ball, so it's say a vibgyor is actually moving, or say a red and blue. So half portion is red colored, half portion is blue colored, and it is like there is an infinite kind of force which is spinning it continuously. Can you tell me what is exactly the color of that ball, or say? Cannot do that. But if I ask you, okay, pause it. Now, whenever I pause it, you can see a particular out. What you can see either a red ball, that is that half you are watching, or you can see a blue ball, that is the other half you are watching, or you can see a combination of red blue, or in the left it is blue, or right it is red. So likewise there are ways. But what if I tell you there is a computing that it came into picture, which is capable of simultaneously hold the properties or say features of all the four possibilities or three possibilities. Let us consider for simplicity that red and blue together, whenever you are saying, is a one combination. Forget about the like red blue or blue red. What if I told you that you can actually do all the possibilities together? That feature is called superposition. So now we are entering into the powers, or say kind of the Avengers behind quantum computing, which is giving it the power that it has, and why we are here for. Okay, so why we are here is basically to explore all the powers that quantum computers have. Basically for that only we are able to like do a lot of computations, or is thinking of certain business outcome, whatever it is, because of these powers. So first power is a superposition. What is superposition? In easy, what is the power of being in multiple states simultaneously? Right? Okay. So in classical computing, a bit can be either a 0 or a 1. I guess I actually, it's 4 p.m. now. So it's up to you. So organizers, if anyone can tell that, should I continue or should I just pause here and continue from tomorrow? Because it's already 4. Then we can start. Because right now we are in a I can continue for a few more, say 10 minutes. If you agree, or if there is no issue, I can continue. I can see one tomorrow, please. No, don't think it as a slides left, because we just completed the base. So right now we will actually we will discuss. Okay, just give me, if possible, just give me 5 minutes so that I can. Uh, okay, 10 minutes is okay tomorrow, please. I'm just optimizing it and making it 5 minutes if possible. So again, we will like discuss at least 5 minutes. We will also put in the tomorrow's class. Whenever we start, then we will continue. Okay, 5 minutes. Yes, please. So one power is superposition. In a very nutshell, I'll just discuss all the names of the at least the powers that quantum have. Then we will discuss in the next class. And actually, we also missed 5 minutes while I was there was a connection cut and all those things. So first is the power of being in multiple states. It can be either a 0, red, a 1, blue, and a combination of 0 and 1. That is a red and blue. You can think it all together. So if you have 5 fingers, okay, you have 5 fingers, I can tell you that, okay, you say finger down is off or 0 and finger up is 1. And you have your 5 fingers. Now, can you think it in this way that with only 5 fingers, you can actually encode, okay, say all the 32 possibilities possible? In what way? Say all the 5 fingers are down, then it's a 0, 0, 0, 0, 0, or a off, 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 off. All the 5 fingers are up, it's a 5 ons. Now, if it is say off, on, off, off, on, it's basically 0, 1, 0, 0, 1. Likewise, you can pick it up. So just think a quantum computer as of now as your hand with 5 fingers, where fingers is nothing but a quantum bit. Okay, it's specific bits. Just like in classical, we have classical bits. So in quantum, it has quantum bits, which is also called qubits. So your 5 fingers are basically 5 qubits, and your hand is a quantum system. Okay, and what is a state? Quantum state, that is say off, on, off, off, on. This is one of the quantum states in very easy words, right? We'll discuss all of these things, don't worry. Second part is entanglement. It is a quantum connection across space. In easy, very easy words, in very easy words, think it of like a Jurua movie of Salman Khan. All of you, I guess, have watched it. It's like there is no logic in that movie, but still it is just like that. If you affect one, if you cause an hit to one person or one particle, or say one unit, anything, so the similar kind of effect as you should see in the outcome of that person that whom you have hit, you will feel or you will see the similar effect on the other person. Are distant apart, they are not really together, they are not communicating with each other anyway. So this is a kind of a entanglement which is very much related to teleportation, but as of now we can think it of whenever this happens, so we will call the two systems or the two particles to be in entanglement with each other. We can do it, we can actually make the logic of entanglement. So when two particles, they are a distant apart, but even after that, yes, even after that, the effect that you can see in one part or one say particle uh, at certain if like distance, the other particle will be behaving in the same way. Now there is correlation. In mathematically we call it correlation. So they are either they are positively correlated or they are anti-correlated. That is, if you say up, make this thing up, it will either be up on the other side or it will be down to the other side. It can happen anyway. But this is a simple theory of an entanglement. Okay. And this is another feature that quantum has. The third one is a quantum interference, which is a dance of probability waves. Now, quantum interference is basically, you can think it of like a, what I will say, it's very mathematical. As of now, say, for example, just the waves, you can see the waves basically, and whenever they are they're colliding two waves. So you can see a certain kind of an interference or pattern. In water, in a water body, maybe a pond or a lake, you can actually feel the same thing happen. When two waves, they collide, we'll see a certain kind of a pattern. Now, what will happen when they collide? Two things can happen. Either some of the their properties will be added. There will be a different kind of waves or amplitudes of wave forming, or it can actually be lost. So anything can happen. Based on that, we call it a constructive interference and a destructive interference, and both has a huge effect whenever we will be doing the computing itself with the logic. You can see the difference. There are a lot of like probabilities, a lot of factors, choices, the number of qubits, how they are related to it, a lot of such considerations is there. Okay, so whenever they are aligned, they will create a bigger wave, which is a constructive one, and whenever they cancel out each other, it will be a disappear, or it is a destructive one. Okay. Okay. Fourth one is a no cloning theorem. No cloning theorem. It's the quantum copying limitation. tomorrow I would love to, if you agree, all of you agree, I would like to again put 5 to 10 minutes for all the features. Then we will start. It will create a good impact, at least with all of you. You will understand it even better. Just remember it in this way, that a no cloning theorem is for quantum, you do not have a Xerox machine. What is a Xerox machine? If you give a paper, it can actually able to clone the content present in the paper. Now, that paper, within that paper, you can write anything, right? Still, your Xerox machine will be able to tell you what is the output. Just like that, in quantum, if you give if you say a quantum Xerox machine, if you give a quantum state, anything, say off, on, 00111, in a quantum Lie setup, if you give it to a quantum Xerox machine, you cannot replicate or you cannot clone the exact state under certain conditions. What is the condition? That you do not know anything a priori. No information is given to you that how you prepared your earlier state. There was no such theory given to you that, okay, I prepared while I was framing the quantum state, these are the things that I was doing. Yeah, I was doing. So all these things you do not have any information about. But if you have the output, you cannot clone the same state 00111. Whatever be its state, it's a 70% of 0 and 30% of 1. You cannot replicate and make a 70% 0 and 30% 1. This is what I am talking about. Okay, so whenever something is in superposition, and there is no way you can actually clone a superposed quantum state if you do not have that context available with you, which is the preparation and the measurement context. If you do not have that contextuality, you cannot really predict cannot really clone the exact state. Okay, so that particular quantum Xerox machine is not available with you. And this is a huge impact whenever you are say for example, you are using it for a safety purpose. Okay, so with every certain information, you are attaching quantum state to it. Now, in a way, say you are using it as a quantum lock, that particular quantum state. Now, if an eavesdropper or an intruder want to put anything with that particular lock, so your data will be maybe intact, but your quantum state will actually change. Okay, that is a key. It's very useful for quantum key distributions and all those things. So you're basically the fundamental, you are using it certain kind of a flag for the receiver to understand that, okay, whether in between the communication, whether your data was really hacked or it was stolen or it was intercepted or it was read, any tampering was done with the data or not, that you can actually check. So here I have given you a practical example of no cloning theorem, or how it is very, very useful for quantum cryptography and all those stuff. Quantum decoherence is a simple thing. Once you have something, it's very quantum systems ideally is not very like kind of resilient in nature. It's extremely fragile. As and when time passes, or your distance in between the two quantum, say, bits. What is quantum bit? I do not know, because I have not told you. Say anything with a quantum unit, if I keep on increasing the distance, its power, its amplitude, it's the way it works, the quantum information uh, present in that particular unit will start diminishing. So it's a way that you have to keep it in mind, that any disturbance will cause information loss for a quantum system. So you have to think it of with a certain kind of an error correction, or certain kind of a way of very strategically putting your logic whenever you are thinking of interacting or making an interaction between two quantum units, so that ultimately there is no information loss. So those kind of like swapping, a lot of rerouting logic you have to apply. That is a logic, but it's a very, very real problem, quantum decoherence. So I have just added in this way, it's an enemy of quantum computation. So it's a challenge in the physical level, which you have to, or the like engineering level, which you have to think it of. So why these principles make quantum computing revolutionary, the superposition, all these things. Now you know these are really not something that we already have in a classical setup, which is a superposition, entanglement, interference, no cloning, and decoherence. There is another very fundamental thing, which is measurement. We will discuss it later. Measurement is that thing where basically if you try to measure it, the quantum property will actually not be further there with you. Okay. So you have to, that is another challenge basically. So the parallel computation, computing simultaneously all possibilities, those will not be possible if you just tamper the quantum system, because it is not clonable, and whenever you try to tamper it, its quantumness will be lost. It will be a quantum state, but that on that very point, it will start behaving as a classical state. So what is next? Transition to 4 quantum computing verticals. Now that we understand the why quantum mechanics is different to classical computing, the next step is explore how these kind of things can be applied in the real world technology. So that was our agenda. We will be all covering it in the multiple sessions, even in QT01. We will be covering a bit of quantum computing and communication. So the 4 verticals are quantum computing, which is a solving quantum problems which a classical computers cannot. You can think it of in this way. It's a computing. It has a quantum algorithms and all those stuff. Then it comes quantum sensing is like sensing quantumly. You can say it in this way. So it's ultra precise measurements, which is beyond your classical limits. Then it's quantum communication, which is unbreakable encryption and secure messaging. And how you do it? We do it through no cloning theorem, as well as entanglement and your yes, entanglement and no cloning. Those are the 2 things. And measurement theory, of course. Even whenever you try to do it, it will be non-quantum at that very point. And quantum simulation is understanding the materials, chemistry and biology at the quantum level. So here is where I want to end. Okay. So any questions anyone wants to ask? And just stop sharing. Anyone, any question you want to ask, you can ask now. I can see a couple of very technical questions. T.S. Guru Raja, how can we reduce the circuit complexity in quantum operation? I guess we are asking for quantum circuit complexity reduction. We will be talking about those things, don't worry. There are, of course, ways through which, I guess, by the term circuit complexity, you want to reduce the quantum gates. If you are asking this, we will be discussing it. Okay. So scaling property, please give the reference. I'm not understanding it. Is quantum computing analog computing? I really don't know what is the relation here with respect to superposition. Okay. Okay. The logical start on the quantum. Great to see such enthusiasm in the participants. Okay. Voice is on first track. Okay. Start. Okay, one question I want to answer. Saloni Vishwakarma, quantum computer can it fully replace classical computer? It can never replace. No matter what the like the sales team from quantum tells you that yes, it can replace a classical computer, it can replace, but it can definitely make your classical system a lot more powerful. There are a lot of threats that quantum is giving, and there are a lot of opportunities also that quantum is giving. So we should know that how to use it very optimally so that we can make a maximum benefit of it. But definitely it's not a replacement kind of thing. Just like an AI, I guess. Still with a chat GPT and all, still you need a human interruption, or you have to use it strategically. So without Sam Altman, there is no ChatGPT. So that is the thing. No, cloning can help in quantum cryptography because, say, for example, you are a hacker, you have a quantum state. Okay, you have a, say, logic. Somehow you are able to get that packets of data, which is a very, say, like considering like, or say, very kind of a sensitive data or something very important data is, say, for example, is going, and you are a hacker, you have that data, you tampered it, so your quantum state, actually what will happen, it will not be the same thing, same quantum state as it was initially. Here it helps that as a hacker you will also not be able to clone that quantum state and again put it in the packet, and as if there was no intruder in between, so that the sender, the receiver will not understand. So in that way it helps. The different approaches are getting started. How can beginner learn and start working with quantum computing? See, IBM is a one-word answer for it. So go to Qiskit and you can learn a lot for that. Okay. What are the current research topics and area of interest? Technically, medical instrumentation. I have to check. What sessions? Scaling property will happen if you increase the number of qubits with quantum bits. You can actually make it more superposed, more number of states into superposition. If you have 5 qubits, it will be 2 to the power 532 number of states. If you want to scale it to more thing in a perfectly say non-decoherent environment, for example, if you increase it or make it say 6, it will be 64. So in that way, you can think of encoding multiple data into the quantum machine just by increasing the number of qubits. So increasing the qubits here is related to the scaling property or scalability. Okay. Lot many platforms are good. So I shouldn't be very specific, but you can check for the quantum computing languages. What are the languages and what platform you can get to that. Okay. Okay. We can pause here. Is PwC planning to use a QC? That depends on the fund that we get. And I'm not in a position to tell, honestly. But currently they are doing something with the D-Wave right now. Very experimental level it's though. Yes, I guess it's covered. So thank you everyone. And it's up to the committee now. Okay. I think you will all will be getting the slides. Sorry about it. I already have shared the slides. We'll be getting it. We'll see how qubits are represented. It's through bracket notation. Yes, sir.
Yeah, thank you so much, ma'am. Thank you for this time. But yeah, some of them have a request that they have to travel at 4 o'clock. Hello.
Yes, sir, you are audible.
Yeah. Okay. So we will try to start on time tomorrow, and then we will also finish at 4 o'clock, and so that they will all not have any issue. We will also ensure that all your login problems, if there are any, we will try to address them. Please contact your respective academies where you are registered. We will sort out because there is a slight mechanism of maintaining the attendance. So the attendance will be maintained through WebEx itself. So please maintain that. And Nivedita ma'am will be very particular. If she has to teach 1.5 hours, she'll teach 1.5 hours. So that's the thought process. Video. So that is where we'll look at. So we will try to wind up today. We will meet at 2 o'clock sharp, and we will start on time, and we'll try to complete on time. Right? Thank you so much.
Thank you, sir.
Yeah, we will share the recording once we will try to take it off, and we'll share it. Ma'am will share the slides with me. I will also share the slides, right? Thank you. Let's go. Yeah. Thank you. We will send the mail mostly by 5 o'clock or 5:30, or maybe today it may get a little delayed. We'll send the mail. Right. Thank you. Thank you, Nivedita ma'am. Thank you, Dr. Ashwath. Have a nice day.
Thank you, Pillai.
Thank you.
You.
Thank you.